Hey there, and welcome back to the Sleepless Scientist. Tonight, we're going to drift off on a journey exploring one of the universe's most profound and beautiful questions. Where does space truly stop? Is there an edge, a boundary beyond which there is simply nothing, or does it simply go on forever, an endless tapestry of stars and galaxies? It's a thought that can make your mind gently wander. Before we dive into the cosmic deep, if you're enjoying these quiet explorations, take a moment to hit that like button and subscribe. It truly helps us keep these starlit stories coming, and we appreciate your company on these late-night adventures. Now, settle in. Our story begins not in the vastness of space, but in a rather ordinary yet remarkable place, Homedale, New Jersey, in the mid-1960s. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs. Their task was to build and test a new kind of antenna designed to pick up incredibly faint radio signals from space. This wasn't just any antenna, it was a massive horn-shaped instrument nearly 20 feet long. It was meant to be incredibly sensitive, perfect for communicating with early satellites. As they began testing, Penzias and Wilson encountered a persistent problem. There was a faint, steady hiss of noise, a low static that seemed to come from every direction. It was subtle, but it was there, no matter where they pointed the antenna. This wasn't the kind of signal they were looking for, and it was certainly not expected. They meticulously checked their equipment. Every wire, every connection, every component was examined. Could it be a malfunction within their sensitive receiver? They even considered more unusual culprits. Pigeons had nested inside the horn antenna, so they cleaned out all the pigeon droppings, hoping this white dielectric material was the source of the interference. But even after a thorough cleaning, the faint hiss remained. It was still there, uniform and unwavering, a cosmic whisper that refused to be silenced. Penzias and Wilson were puzzled. This wasn't a local issue, like radio interference from a nearby city. This noise truly seemed to come from beyond Earth, from every corner of the sky. Around the same time, just 30 miles away at Princeton University, a group of researchers led by Robert Dick and including Jim Peebles, Peter Roll, and David Wilkinson were working on a different problem. They were theorizing about the very beginning of the universe. Specifically, they believed that if the Big Bang theory was true, there should be a lingering afterglow of radiation. This afterglow of faint microwave radiation would be a relic from a time when the universe was incredibly hot and dense. They were actually building their own antenna to try and detect it. When Penzias and Wilson heard about the Princeton group's work, a light bulb slowly began to glow. Could the persistent noise they were detecting be this very afterglow? The pieces clicked into place. What they had stumbled upon was not interference, but a profound echo of creation itself, the cosmic microwave background, or CMB. It was like looking at a baby picture of the universe taken when it was only about 380,000 years old. Imagine seeing the universe as it truly was so incredibly long ago. To understand this, we need to go back even further. In its earliest moments, the universe was a superheated, dense fog, a plasma of fundamental particles. Light particles, or photons, couldn't travel freely. They were constantly scattering off electrons, trapped in this cosmic soup, unable to escape. But as the universe expanded, it also cooled. After roughly 380,000 years, it had cooled enough for electrons and protons to combine, forming the first stable atoms. Suddenly, the universe became transparent. The photons, once trapped, were now free to travel across the cosmos, carrying with them the imprint of that moment. This ancient light, stretched and cooled by billions of years of cosmic expansion, is what we now detect as the cosmic microwave background. The remarkable thing Penzias and Wilson observed was its uniformity. The CMB was almost perfectly smooth, the same temperature in every direction they looked. This uniformity suggested that the early universe at that moment of transparency was incredibly smooth and homogeneous, a calm, even canvas. But as scientists continued to study the CMB using more advanced instruments, they found that it wasn't perfectly smooth. There were tiny, almost imperceptible fluctuations. These subtle temperature differences, measured in millionths of a degree, were incredibly significant. They were the earliest seeds of everything we see today. Imagine these fluctuations as tiny ripples in the cosmic ocean. Over billions of years, gravity began to amplify these ripples, pulling matter together in the slightly denser regions. These slightly denser areas grew larger, eventually forming the first stars, then galaxies, and finally, the colossal clusters of galaxies that populate our universe. The CMB, therefore, not only confirmed the Big Bang theory, but also provided a blueprint for the large-scale structure of the universe. It showed us that our universe is fundamentally flat in its geometry, meaning that parallel lines remain parallel, much like a flat sheet of paper, rather than a curved surface. This flat geometry has profound implications for how the universe expands and how it might ultimately evolve. It's a key piece of information in our cosmic puzzle. From a seemingly annoying hiss in a radio antenna, we gained our first true look back in time, directly witnessing the universe's infancy. The CMB is a constant, gentle reminder of our cosmic origins, a soft glow that surrounds us, even as we sleep, a relic from nearly 14 billion years ago. This ancient light tells us so much about the universe's early moments, its composition, and its shape, but it also raises deeper questions. If this light comes from the edge of the observable universe, what lies beyond that edge? Does the universe simply continue unseen? And if the universe is flat and expanding, does that mean it stretches out infinitely without end? Or is there a different kind of boundary, one we can't yet grasp? The discovery of the CMB was our first step into truly understanding the vastness of space and its history. It opened a window to a time before stars, before galaxies. But the question of where space stops, of its ultimate nature and boundaries, remained a profound mystery, beckoning us further into the cosmic night. And it is this mystery that will guide our journey through the rest of our quiet exploration, as we drift deeper into the universe's most curious questions. Our journey through the cosmos continues past the ancient glow of the cosmic microwave background. That uniform whisper of creation showed us the universe's infancy, but it also hinted at limits, at horizons of light. To truly understand these limits, we must step back in time to the early 20th century. Astronomers then faced a profound puzzle, one that shaped our very understanding of the universe's scale. The night sky was filled with fuzzy patches of light, often called nebulae. Some were clearly gas clouds within our own Milky Way, but others, like the Andromeda Nebula, were different. Their spiral shapes hinted at something grander. The great debate of the time revolved around these spiral nebulae. Were they simply clouds of gas and dust within our galaxy, or were they island universes' vast star systems, much like our own Milky Way, but incredibly distant? This question was not merely academic. It dictated whether our universe was a solitary island of stars or one of countless similar islands scattered across an unimaginable void. The scale of everything hung in the balance. To resolve this, astronomers needed more powerful eyes. They needed telescopes capable of discerning individual stars within these distant, fuzzy patches. The limit of their instruments was the limit of their knowledge. High above the smog of Los Angeles on Mount Wilson stood the most powerful telescope of its era, the 100-inch Hooker telescope. It was a marvel of engineering, a giant eye pointed at the heavens. This instrument would become the stage for one of astronomy's most pivotal discoveries, a moment that would forever reshape our understanding of space's true extent. In the 1920s, a quiet, meticulous astronomer named Edwin Hubble arrived at Mount Wilson. He was determined to use this colossal instrument to settle the nebula debate once and for all. Hubble possessed a unique blend of observational skill and interpretive genius. He knew that finding specific types of stars within the nebulae would be the key to unlocking their true distances. His focus turned to the Andromeda Nebula. Night after night, he exposed photographic plates, patiently collecting faint light from this distant swirl. On one particular plate taken in October 1923, Hubble found what he was searching for, a tiny, flickering star. He marked it with an N for nova, a star that suddenly brightens. But upon closer inspection of other plates, he noticed something remarkable. This nova was not a one-time event, it was a Cepheid variable star. These stars pulsate with a predictable rhythm. The brilliance of Cepheid variables lies in their unique property. Their pulsation period is directly related to their intrinsic luminosity. Brighter Cepheids pulse slower, dimmer ones faster. This meant that if you could measure a Cepheid's pulsation period, you knew its true brightness. Then, by comparing that to its apparent brightness from Earth, you could calculate its exact distance. Hubble painstakingly observed several Cepheids in Andromeda. His calculations were revolutionary. The distances he derived were far, far greater than anything previously imagined. Andromeda was not a cloud within our galaxy. It was another galaxy entirely, millions of light years away. The universe was suddenly, overwhelmingly larger than anyone had conceived. This discovery shattered the old view of a solitary Milky Way. Our galaxy was just one of countless island universes, each a swirling collection of billions of stars. Hubble didn't stop there. He began to measure the distances to other spiral nebulae. Simultaneously, other astronomers, notably Vesto Slipher, had been measuring their redshifts. Redshift is like the Doppler effect for light. If a light source moves away from you, its light waves are stretched, shifting towards the red end of the spectrum. If it moves closer, they shift to blue. Slipher had found that most spiral nebulae were redshifted, meaning they were moving away from us. But the significance of this wasn't fully grasped until Hubble connected the dots. Hubble, with his assistant Milton Humason, combined his distance measurements with Slipher's redshift data. The pattern was unmistakable and profound. The farther away a galaxy was, the faster it appeared to be receding from us. This wasn't a random motion, it was a systematic expansion of space itself. This realization, now known as Hubble's law, provided the first observational evidence for an expanding universe, a concept that had only recently emerged from theoretical physics. Imagine dots on the surface of an inflating balloon. As the balloon expands, the dots move farther apart from each other, but no single dot is at the center of the expansion. Similarly, galaxies are not moving asterisk through asterisk space, but asterisk with asterisk space as it expands. Everything is moving away from everything else on average. This expansion means that the light from very distant galaxies has been traveling for billions of years, stretched and reddened along its journey. And this brings us to the concept of the observable universe. It is not a physical boundary in space, but a horizon of light and information. Light travels at a finite speed. Since the Big Bang, roughly 8 billion years ago, light has had only that much time to reach us. So, when we look out into the cosmos, we are also looking back in time. The most distant objects we can see are those whose light has just reached us, having traveled for nearly 8 billion years. This defines our observable universe, a sphere roughly 46.5 billion light-years in radius centered on us. But why 46.5 billion, not 13.8 billion? Because while the light was traveling, the universe was also expanding. The space between us and that distant galaxy stretched, carrying the galaxy even farther away. So, a galaxy whose light took 13.8 billion years to reach us is now much, much farther away. It's like a message sent from a ship that keeps sailing away as the message travels. The edge of our observable universe is therefore not a physical wall, but simply the limit of how far light has had time to travel to us since the universe began. Beyond this horizon, there is almost certainly more universe, more galaxies, more stars. We just can't see them yet because their light hasn't reached us. In fact, some objects beyond our observable horizon are moving away from us faster than the speed of light, due to the expansion of space itself. This doesn't violate Einstein's theory of relativity, which states that nothing can move through space faster than light. Here, it's space itself that is stretching. So, the edge of the observable universe is a boundary of information, a cosmic horizon. It's a snapshot of the universe as it was, not as it is now. This horizon is constantly expanding as more light reaches us, but it also means there are parts of the universe we may never see, forever beyond our reach. But if our observable universe has a horizon, what about the universe as a whole? Does it have an edge, or does it stretch infinitely, a boundless expanse waiting to be imagined? Our journey through the cosmos has revealed the observable universe, a sphere of light reaching us from 13.8 billion years ago. But this is just one kind of horizon, defined by what light has had time to reach us. There is another, more profound boundary, one that speaks not of our past view but of our future knowledge, the cosmic event horizon. It's a limit to what we will ever be able to see. The particle horizon, as we discussed, marks the edge of what light has reached us since the Big Bang. It expands as more time passes, allowing more light to arrive. The cosmic event horizon, however, is different. It defines the maximum distance from which light emitted today will ever reach us, even if we wait for an infinite amount of time. This distinction became critically important in the late 20th century, as astronomers began to probe the universe's expansion with unprecedented precision. The prevailing wisdom held that gravity should be slowing things down. For decades, the standard cosmological model predicted that the universe's expansion, initiated by the Big Bang, must be decelerating due to the gravitational pull of all the matter within it. Scientists were diligently working to measure this expected slowdown, to quantify precisely how much gravity was braking the cosmic expansion. The method involved observing distant type Ia supernova. These stellar explosions are incredibly bright and, crucially, possess a remarkably consistent intrinsic luminosity. Because of this consistency, type Ia supernova are often called standard candles. By comparing their observed brightness to their known intrinsic brightness, astronomers can accurately calculate their distance. In the mid-1990s, two independent research teams embarked on this ambitious quest: the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, co-led by Brian Schmidt and Adam Rees. Their task was painstaking. They needed to find these rare supernova in very distant galaxies, requiring long exposure times and powerful ground-based and space telescopes. Night after night, they scanned the skies, collecting faint photons from explosions that had occurred billions of years ago. Each new detection was a precious data point. As the data accumulated, a perplexing pattern began to emerge. The distant supernova were not behaving as expected. they appeared fainter than they should have been. Fainter meant they were farther away, and if they were farther away than predicted, it implied that the universe's expansion had not been slowing down as expected. Initially, there was a natural skepticism. Could there be an error in their measurements? Was there some unknown cosmic dust dimming the light? They meticulously checked every variable. But both teams, working independently with different data sets and analysis methods, arrived at the same astonishing conclusion. The universe's expansion was not decelerating. It was, in fact, accelerating. A profound cosmic force was actively pushing galaxies apart, overcoming gravity's pull. This mysterious force was given a name: dark energy. Its discovery in 1998 sent shockwaves through the scientific community, completely rewriting our understanding of the universe's fate. The implications for our cosmic horizons were immediate and unsettling. An accelerating universe profoundly changes what we can and will ever observe. If the expansion continues to accelerate, then distant galaxies are not merely receding from us. Their recession velocity is increasing over time. This means that light from some galaxies, even if emitted today, will never reach us. The space between us and them is stretching too rapidly, like a river flowing faster than a swimmer can cross. These galaxies are effectively moving beyond our cosmic event horizon. They are not just out of sight today, they will be forever beyond our future sight. As eons pass, more and more galaxies will cross this boundary. Our observable universe, while still expanding in terms of its particle horizon, will become increasingly barren. The light from these receding galaxies will be stretched to such extreme wavelengths that it becomes undetectable or simply never arrives at all. They become truly isolated. This is a profound and somewhat melancholic realization. Future astronomers, billions of years from now, may look out into a nearly empty sky, seeing only our own local group of galaxies. The cosmic event horizon defines the ultimate limit of our knowledge about the universe beyond our immediate vicinity. What lies beyond it becomes forever unknowable. The discovery of dark energy introduced the dark energy dilemma. What is this mysterious force? Where does it come from? Its nature remains one of the greatest puzzles in science. Is it a property of space itself, a cosmological constant as Einstein once proposed? Or is it a dynamic, evolving field, something called quintessence? The answer to this question will determine the ultimate fate of the universe. Will it expand forever, leading to a cold, dark Big Freeze? Or will dark energy eventually become so powerful that it tears apart galaxies, stars, and even atoms in a catastrophic Big Rip? For now, dark energy continues to accelerate the universe's expansion, pushing galaxies beyond our event horizon, forever out of reach. This means that the universe we observe today, rich with countless galaxies, is a fleeting snapshot. Our cosmic view is already diminishing, albeit on timescales far beyond human comprehension. The cosmic event horizon is a boundary of ultimate despair for future astronomers, a limit to what they can ever hope to learn about the universe's grand scale. It forces us to confront the humbling reality that even with infinite time, there are parts of the universe we are destined never to know, never to see. This accelerating expansion also raises profound questions about the very nature of space itself. If it's stretching, what is it stretching into? And if our observable universe is just a tiny part of a much larger, unseen cosmos, what does that imply about the ultimate size of everything? The very idea that parts of the universe are forever beyond our reach, not because of distance or time, but because of the fabric of space itself, is deeply thought-provoking. It suggests a universe far grander and perhaps far stranger than our current observations can encompass. Our horizons are not just about light, but about fundamental limits. The accelerating universe, driven by dark energy, has redefined our understanding of cosmic boundaries. It has opened a door to questions about what lies beyond our current perception. And it is these profound questions about unseen futures and the nature of cosmic limits that gently lead us towards even more speculative and fascinating realms, the possibility of universes beyond our own. The accelerating universe, driven by dark energy, has redefined our understanding of cosmic boundaries. It has opened a door to questions about what lies beyond our current perception. We are drawn to the idea of an edge, a definitive stopping point. This human inclination to define limits is ancient, stretching back to early philosophical inquiries. For centuries, thinkers pondered the nature of the cosmos. Was it a finite container like a grand, celestial box, or did it stretch endlessly without end? The concept of infinity was both fascinating and unsettling. How could something simply continue without ever reaching a boundary? Our minds struggled with this abstraction. Consider the Earth. For early navigators, the ocean seemed to stretch infinitely. Yet they eventually understood it was finite, though without a discernible edge in the way we usually imagine. A ship sailing west would eventually return from the east. The surface of our planet is finite, but it is also unbounded. There is no edge where you can fall off. This simple yet profound idea offers a powerful analogy for the universe. Could space itself be finite, yet still have no boundary? This is where the concept of cosmic topology emerges. It asks, what is the overall shape of the universe? Could it be like a cosmic sphere or a donut shape or something even stranger? In such a universe, if you traveled in a straight line for long enough, you might eventually return to your starting point without ever having encountered a wall or an edge. It's a universe that loops back on itself, a vast, self-contained canvas with no external boundary. This concept is both elegant and mind-bending. The advent of non-Euclidean geometry in the 19th century provided the mathematical framework for such possibilities. Space wasn't necessarily flat, as Euclid had assumed. Mathematicians like Riemann explored geometries where parallel lines could converge or diverge, where the sum of angles in a triangle wasn't always 180 degrees. These abstract ideas laid the groundwork for a revolutionary understanding of space itself, moving beyond our everyday, intuitive perceptions. Then came Albert Einstein's general relativity in the early 20th century, which fundamentally transformed our view of space and time. Einstein showed that spacetime is not a static, inert stage upon which cosmic events unfold. Instead, it is a dynamic, flexible entity, interwoven with matter and energy. Gravity, in this view, is not a force pulling objects together, but rather the manifestation of mass and energy curving the fabric of spacetime around them. This means the universe doesn't exist in a container, it is the container, and its shape, its geometry, is determined by its total energy density. General relativity allows for three fundamental geometries for the universe as a whole: flat, positively curved like a sphere, or negatively curved like a saddle. A positively curved universe would be finite and unbounded, much like our Earth's surface. Travel far enough and you'd return to where you started. A negatively curved universe would be infinite, like an endless saddle. And a flat universe, as suggested by the cosmic microwave background data, would also be infinite. The CMB, with its tiny temperature fluctuations, tells us that the universe's overall geometry is incredibly close to flat. This has profound implications for its ultimate size. If the universe is truly flat, then it is infinite. There is no edge, no boundary to be found because there is simply more space continuing indefinitely. This challenges our intuitive need for a boundary, for a place where space stops. It suggests a reality far grander and more boundless than our minds can easily visualize. Imagine a universe where every point is surrounded by an infinite expanse. No matter how far you travel, there is always more, an unending tapestry of cosmic structures. This infinite flat universe is the simplest and most consistent model with our current observations, particularly the precise measurements of the CMB. But even in an infinite universe, our observable universe remains finite, constrained by the speed of light and the age of the cosmos. Beyond our horizon, the universe continues, unseen, perhaps with countless galaxies identical to our own or entirely unique ones. The implications of an infinite universe are staggering. If space truly extends forever, then every possible arrangement of matter and energy must eventually repeat. Somewhere infinitely far away, there might be another Earth, another you, living out an identical life, or perhaps a slightly different one. This isn't a mystical idea, but a logical consequence of an infinite space with a finite number of particle arrangements. The universe in this view is not a confined space struggling against a boundary, but an ever-unfolding canvas, rich with possibilities. It means the question "where does space stop?" might be fundamentally flawed. Perhaps space simply is without a stopping point. The concept of an edge implies something beyond the edge. But if space is infinite, there is no beyond in that sense, there is only more space. This shift in perspective from a bounded cosmos to an unbounded one marks a profound evolution in our understanding of reality. It moves us from a universe that might be contained within something larger to a universe that is itself the ultimate expanse. Yet even an infinite universe doesn't fully satisfy all our curiosities. What if our universe, vast as it may be, is not the only one? What if the very fabric of existence is not a single, continuous canvas, but a collection of distinct, perhaps even disconnected, realities? This idea, once relegated to science fiction, is now a serious area of scientific inquiry, emerging from the depths of quantum mechanics and cosmological theories. The boundaries we've explored so far, the CMB, the observable universe, the event horizon, all pertain to our universe. But what if the true edge lies not within space, but between different spaces, different realities? This is the realm of the multiverse, a concept we will gently explore next. The accelerating universe, driven by dark energy, has opened a door to questions about what lies beyond our current perception. We considered how our universe might be infinite, yet still, the whispers of something more profound began to emerge. What if our universe, vast as it may be, is not the only one? This idea, once a flight of fancy, has matured into a serious area of scientific inquiry, the multiverse. The journey into the multiverse begins not in distant galaxies, but in the peculiar world of quantum mechanics, a realm governing the smallest particles of reality. In the mid-20th century, physicists grappled with quantum paradoxes. Particles seem to exist in multiple states at once, only deciding their reality upon observation. The standard view, the Copenhagen interpretation, suggested that observation collapsed these possibilities into a single outcome, but this felt unsatisfying to some. A young Princeton graduate student named Hugh Everett Roman III in the late 1950s proposed a radical alternative. What if the wave function never truly collapsed? Everett's many worlds interpretation suggested that every quantum possibility actually happens. Each measurement, each interaction causes the universe to branch. Imagine a single electron. When its spin is measured, it could be up or down. In Everett's view, the universe splits into two branches. In one branch, the electron is up and we observe it as up. In another, equally real branch, the electron is down and a different us observes it as down. This means our reality is just one of countless branches, each representing a different sequence of quantum outcomes, an infinite cosmic tree constantly growing new limbs. Initially, this idea was met with deep skepticism. It seemed too fantastical, too extravagant to be a serious scientific theory, but it elegantly solved some quantum puzzles. The observer problem: how consciousness affects quantum reality, simply vanishes. The observer is merely part of the branching, not causing a collapse. The philosophical weight of this was immense. It suggested that every decision, every possibility, truly exists somewhere in some other universe. But quantum mechanics wasn't the only path to the multiverse. Another, equally compelling route emerged from the realm of cosmology itself. Recall the theory of cosmic inflation proposed in the early 1980s. It described a period of extraordinarily rapid expansion in the universe's infancy. Inflation elegantly explained several cosmic puzzles, like the universe's flatness and the uniformity of the cosmic microwave background. As cosmologists like Andre Linde refined inflationary theory, a startling implication arose. Inflation might not have a single, definitive end. Instead, inflation could be eternal. Once it starts, it might continue indefinitely in some regions of space while ending in others. These regions where inflation ends would bubble off, forming distinct, self-contained universes within a larger, inflating metaspace. Our universe in this eternal inflation model is just one such bubble, and there would be an infinite number of these bubble universes, constantly forming. Each bubble might have started with slightly different initial conditions, or even different fundamental physical constants. This level Roman II multiverse, as classified by physicist Max Tegmark, suggests a vast cosmic landscape far beyond our single observable bubble. Tegmark's classification provides a helpful framework for these grand ideas, moving from the merely unobservable to the truly distinct. He described 4 levels of multiverse, each more encompassing than the last, and each with its own compelling scientific basis. Level I is simply our infinite universe, extending beyond our observable horizon. If space is truly endless, then everything that can happen eventually will. This means somewhere out there, beyond what we can ever see, are other regions of space identical to ours, perhaps even containing exact copies of ourselves. Level Roman II is the eternal inflation multiverse, the bubble universes we just explored, arising from the ceaseless process of inflation. These bubbles could have different physical laws, different values for fundamental constants, making them truly distinct from our own. This offers a possible explanation for why our universe seems so fine-tuned for life. We simply happen to be in one of the bubbles where conditions are right. Level Roman III brings us back to quantum mechanics, the many worlds interpretation. Each quantum choice branches our universe into new, parallel realities. The key difference is that level Roman II multiverses exist in different space-time regions, while level Roman III multiverses are parallel realities existing in the same space-time but decohered from each other. Finally, level Roman IV is the most abstract, the mathematical universe hypothesis. It posits that all mathematically consistent structures exist as universes. Our universe in this radical view is simply one particular mathematical structure, and every other possible mathematical structure is also a universe. This would mean that the very laws of physics we observe are not fundamental, but merely the properties of our particular mathematical reality. The challenge, of course, is how to observe or prove the existence of these other universes. They are, by definition, beyond our direct reach. Some theories suggest faint, indirect clues, perhaps a slight gravitational imprint from a collision with another bubble universe in our early cosmic history. A mysterious cold spot in the cosmic microwave background has been a tantalizing, though unconfirmed, hint for some, but definitive proof remains elusive. The multiverse shifts our perspective from a unique, singular cosmos to an ensemble, a cosmic tapestry woven from countless realities. It's a humbling thought that our vast universe might just be one small patch in an unimaginably grander existence, an endless collection of possibilities. This journey into the multiverse leaves us with a profound sense of wonder and a new lens through which to consider the ultimate question. If there are countless universes, where does existence itself truly stop? It's a question we'll quietly ponder as we conclude our cosmic exploration. Our cosmic journey nears its gentle close, but the echoes of its grandest questions still linger. If there are countless universes, where does existence itself truly stop? We've traveled far from a cosmic whisper to the edge of imagination. We began with the cosmic microwave background, the universe's soft, ancient lullaby. It was our first true glimpse into creation, a uniform glow from nearly 14 billion years ago, revealing our universe's infancy. Then we navigated the boundaries of our observable universe, a horizon defined not by a physical wall, but by the finite speed of light. It showed us what light has had time to reach us, a snapshot of the past. We then confronted the accelerating expansion, driven by dark energy and the cosmic event horizon. This unsettling boundary suggests parts of the universe will forever recede beyond our future sight, becoming unknowable. We explored the idea that space itself might be finite yet unbounded, like the surface of our planet, a universe that loops back on itself without a physical edge to fall off. And then the profound implications of a flat universe as suggested by the CMB. If truly flat, space stretches out infinitely, a boundless expanse where stopping has no meaning. Finally, we ventured into the multiverse, born from quantum mechanics and eternal inflation. Our universe perhaps just one bubble in an endless, frothing cosmic ocean of possibilities. From the smallest quantum fluctuations to the grandest cosmic tapestry, our quiet journey has spanned nearly unimaginable scales of time and space. It has been a humbling and exhilarating exploration. The initial question, where does space stop, arose from a very human desire for limits, for a clear boundary to existence. Our minds naturally seek definition. But as our instruments grew sharper and our theories deepened, the question itself began to transform. It evolved from a simple geographical query to a profound philosophical inquiry into reality's very nature. To ask where space stops is to imply an outside, a region beyond space itself. But what if space isn't a contained entity, but the totality of what exists? The universe, in this evolving view, is not a box or a sphere sitting within something larger. It is the canvas, the fabric, the very framework of reality. Just as the surface of our Earth has no edge yet is finite, so too could our universe be, a journey without end, yet not necessarily infinite in volume. The precise measurements of the cosmic microwave background strongly suggest our universe is geometrically flat, and a flat universe in its simplest form extends infinitely. If truly infinite, then there is no boundary, no ultimate stopping point to be found, only more space stretching endlessly, forever unfolding. Even our horizons, born of light and time, are not static walls. The universe's accelerating expansion means these perceived boundaries are dynamic, ever-changing, and relative to our vantage point. Cosmic horizons are limits to information, to what we can observe or ever hope to observe. They are not physical barriers where space abruptly ceases to be. And in the multiverse, stopping becomes even more abstract. It's not about an edge, but perhaps about transitions between distinct realities, each a universe unto itself. The question transforms from locating an edge to understanding the fundamental nature of existence itself. What defines reality if it can be infinite or manifold? This profound shift in perspective from a contained universe to an unbounded or multifaceted one is perhaps the most significant discovery of all. It humbles us and expands our minds. Yet, through all these conceptual shifts, the human drive for exploration remains. That quiet, persistent curiosity, the need to understand, continues to burn brightly within us. It is this drive that led Penzias and Wilson to clean their antennae, Hubble to measure distant stars, and cosmologists to probe the accelerating universe. The simple act of asking why. From a faint, annoying hiss in a radio receiver to the revelation of dark energy pushing galaxies apart, our journey has been a testament to patient observation. Each answer, rather than closing the book, simply opens a new chapter, revealing a deeper layer of mystery. The cosmos is an endless source of inquiry. There is a profound humility in realizing the vastness of what we still don't know. Our knowledge is but a tiny island in an ocean of cosmic unknowns. But in this humility, there is also immense beauty, the beauty of the ongoing quest, the shared human endeavor to grasp the universe's secrets, one gentle step at a time. Across the globe, in quiet laboratories and beneath vast observatories, scientists continue their work. They are the sleepless minds, patiently piecing together the cosmic puzzle. This collective human endeavor, spanning generations, connects us all. We are inheritors of ancient wonder and pioneers of future understanding. The sheer complexity of the universe, from the quantum foam to the grandest superclusters, fills us with a sense of awe, a quiet, profound wonder. It is this wonder that fuels the persistent spark of inquiry, ensuring that even as we find answers, we will always seek deeper truths, reaching further into the cosmic night. And so, as our journey comes to its gentle close, we return to the quiet of our own thoughts, letting these grand ideas settle softly within us. The cosmos, vast and mysterious, stretches far beyond our current grasp, a boundless tapestry woven with dark energy and untold possibilities. Its humbling scale reminds us of our fleeting place, a tiny moment in the grand cosmic narrative. Yet our capacity to ponder it is boundless. But in this vastness there is profound beauty, the beauty of the laws that govern it, the elegance of its structures, the sheer audacity of its existence. The beauty of discovery, of understanding a little more each day, even if that understanding reveals only greater depths to explore, is a reward in itself. There is a quiet joy in simply pondering these grand questions, in letting our minds wander through the infinite possibilities of space and time. The universe does not owe us simple, definitive answers to questions like where does space stop? It offers instead a more complex, richer truth. It offers an endless tapestry of wonder, a continuous invitation to explore, to question, to marvel at the intricate dance of creation and expansion. The journey itself is the answer, the pursuit of knowledge its own reward. For in seeking the edges of space, we find only the boundless potential of our own minds. And so, as the moon climbs high, sleep well. May your dreams be filled with a mind full of stars and a heart full of peaceful wonder, knowing the universe's mysteries are a gentle, infinite embrace.